I am your moderator. My name's Taryn Schiller, and I'm your cloud senior software lead from Avaya, based in Galway. So on that note, let's welcome our guest speaker today. We have Ken Power joining us. He's actually in America at the moment on a trip, so thanks for joining us so early today, Ken. Ken is an AI software engineer and researcher focused on autonomous vehicles. He has worked with and led global cross-functional engineering teams in full life cycle development of products in multiple segments in companies from startups to Fortune 50s. He also lectures with National University of Ireland, Galway, and is a researcher with LERO, the Science Foundation Ireland Research Centre for Software. Until recently, Ken was an independent consultant working with several companies around the world. And today, as of today, March 16th, he starts a new role with Motional as Director of Engineering to help create self-driving vehicles. Motional is an American autonomous vehicle company founded in March 2020 as a joint venture between automaker Hyundai Motor Group and also supplier Aptiv. Ken is responsible for leading teams working with AI, software engineering, systems engineering, and robotics. So what you can expect from our session today with Ken is we'll look at the intersection of AI and software engineering in modern product development with autonomous vehicles as an example. We would explore some use cases, architectures, and technology stacks, together with some current challenges and research directions. So on that note, I'm going to leave you up on stage here, Ken, and yeah, I'll come back to lead the Q&A a little bit later. Thanks for joining us.
Thank you, Taryn. Okay, I'm going to try and share my content here. Okay, apologies, just a moment. So can you see my shared screen okay?
Yeah, looks good.
Okay, awesome. Okay, so thank you, Taryn, for the introduction, and hello, everybody. Welcome to today's session. We're going to look at the intersection of AI and software engineering in autonomous systems, and we'll be using self-driving cars, mobile robots, autonomous systems as the example backdrop and use cases for a lot of the topics that we'll talk about under the heading of AI and software engineering. So for me, some of the most exciting developments in machine learning and deep learning today are happening in the world of autonomous vehicles. We've got software engineers, data scientists, AI researchers, roboticists, hardware engineers, all coming together to create something that's really incredibly exciting. So for me, it's one of the places to be in terms of applying technology. So as a precursor to some of the things that we'll look at, I'll make a prediction. So, think about this as we move through some of the content and some of the use cases that you'll see today. So the prediction is basically that within the next decade, we'll see major world cities, a selection of major world cities, ban or limit the use of manually driven vehicles. And why might they do that? Well, we'll look at some of the reasons why they might do that in just a moment, and then we'll look at some of the technologies that are enabling that. But really, autonomous vehicles have been on the rise over the last number of years. The convergence or confluence of AI, software engineering, deep learning has really started to accelerate growth in this whole area. And there are some reasons why this is a particularly worthwhile area to explore. For me, number one is safety. If we think about the number of road deaths that are that take place each year, that's something like 38,000 people each day are killed on roads around the world, killed or injured or otherwise affected by traffic accidents around the world. And one of the advantages of bringing AI to autonomous vehicles is that self-driving autonomous vehicles don't get distracted or drowsy or drunk or otherwise compromise to the road conditions around them. So safety of other road users, pedestrians, cyclists is number one, and saving lives. Second reason why we might be interested in autonomous vehicles is the use of space in our cities, in our communities. And you can see the example there is from the city of Dusseldorf in Germany. Over the last 20 years or so, they've managed to reclaim a lot of space that was used by roads and by parking spaces and convert that to more community-led green spaces for the benefit of the people and communities in the city. So in large cities around the world, there's a staggering amount of physical space devoted to car parks and to road traffic infrastructure that can be reclaimed if we move towards a model of embracing more autonomous vehicles and shared ride vehicles rather than individual vehicle ownership. If we think about our typical commute to work, when we have typical commutes to work and we're not in COVID times, our cars spend a significant amount of time parked outside either our home or our office. We drive from our home to our office and from our office back to our home, and cars spend maybe 10% of their utilization in transport and maybe 80 to 90% of their utilization parked. So we have opportunities to better reclaim that space and make better use of it. In the previous talk, we heard a lot about energy use in general, and certainly there's a confluence of autonomous vehicles, self-driving cars, AI and software engineering converging with electric vehicles, and there's a real opportunity to better utilize the energy resources of the planet in the context of self-driving cars, autonomous vehicles. Fourth reason is mobility. So when I talk about autonomous vehicles and self-driving cars, I'm not against driving. I love driving. I know a lot of people who love driving, but there are a lot of people who are unable to drive for various reasons. And so for me, autonomous vehicles opens up mobility options to a lot of people for whom mobility options otherwise wouldn't be as easily available. And we can think about our aging population who may not be in a position to drive continuously throughout their lives, people who are injured or otherwise infirmed or disabled, who are normally not able to drive manually driven cars. Autonomous vehicles open up a lot of mobility options for a lot more people in our communities, and therefore enable a lot more opportunities for connection. And utilization we've touched on already. I talked about how cars spend a lot of time parked either outside our homes or outside our workplaces, and through a model of shared vehicle ownership and what we'll talk about in a few moments in terms of robo-taxis or other ride-share models, we have an opportunity to reduce the need for all of the car parking spaces in our cities and make better use of the space. So throughout the next half hour or so, we'll take a look at autonomous systems. We'll look at some of the problems that AI and software engineering are solving in this space. We'll look at a couple of use cases. We'll look at specifically going from an example problem in autonomous vehicles, looking at how AI and software engineering are applied to address those use cases. We'll spend some time looking at architecture and technology stacks in this space, and we'll look at how software engineering is enabling the AI advances that we're seeing in autonomous vehicles and other spaces. And finally, we'll take a look at some challenges that make this an exciting and interesting area to be, and some of the challenges that are still ongoing in this space. And throughout the talk, we'll touch on some of the research directions that are active in this space. So as Taryn said, feel free to ask questions, and we'll cover as many of them as we can at the end of the session. So before we get into an example use case, I like this. It's useful to have a working definition of intelligence. So we're talking about artificial intelligence. What do we mean in this context by intelligence? And I like Francois Chollet's definition of intelligence here. He says that intelligence is the efficiency with which learning systems turn experience and prior knowledge into skill that previously unknown tasks. And therefore, measures of intelligence need to account for prior experience, generalization difficulty, and so on. And all of these things come into play when we talk about autonomous vehicles navigating the world, interacting with people, interacting with other vehicles. If we talk about artificial intelligence being applied to something like driving, that has to account for helping machines to develop skills at previously unknown tasks in driving. So very short background on AI for anybody that's not familiar with the space. We talk about AI in general, artificial intelligence, as computer systems being able to perform tasks that normally require human intelligence. So an artificially intelligent vehicle, for example, needs to be able to perform tasks that normally a human driver would be. We can think of machine learning then as a subset of artificial intelligence, where we automatically learn and improve from data. We'll talk about the importance of data in this context in a few minutes. And then deep learning as a subset of machine learning. So deep learning is the space where we use artificial neural networks to identify complex patterns of data. And we'll, again, look at some examples of those in just a moment. There are different types of problems we want to solve with machine learning in particular and deep learning. And you'll see those largely broken down into supervised learning, unsupervised learning, and reinforcement learning, with supervised learning further breaking down into things like classification problems or regression problems. And we won't spend a lot of time talking about the details of this, but it's just useful to have that vocabulary as we move into the session on AI and software engineering. So with supervised learning examples, we might be looking at, for example, spam filters, giving lots of labeled email, some labeled as spam or not spam. We can develop systems that learn to identify spam in email, or given a data set of patients that are diagnosed as either having diabetes or not, we can teach our AI systems to learn to classify new patients that either have diabetes or not. So we're feeding the system examples and it's learning. With unsupervised learning, we have an example where we might give the system that we're developing lots of news articles found on the web, through Twitter or LinkedIn or the RTE website or Financial Times website, and to ask the system to group them into sets of articles about the same story. Another example might be, given a database of customer data, we might be looking to identify new customer segments or have the system group customers into similar market segments. And regression briefly then is the task of predicting a continuous quantity, and classification is the task of predicting a discrete label. So given a picture of animals, we might want to say, is there a dog in this picture or not a dog in this picture? Or identify dogs, horses, cats, cows in a particular image of animals. So regression and classification problems are something we'll talk about in the context of autonomous vehicles. In deep learning then, so we talked about deep learning being a subset of machine learning and AI. Think about deep learning simply as being about deep layers of neural networks that are used to represent a problem space. And very briefly, we can see the circles here represent neurons in our deep neural network, and you can see the deep layers of the neural network going from left to right. If we pass in an image of a car, that will pass through the various layers of our neural network, and it will ultimately identify the car as maybe a Hyundai Ioniq 5, for example. And we can inspect each of the layers of the deep neural network and see that through successive layers of the network, the network is pulling out different features of the car. It's learning different features, maybe what a wheel looks like or what a window looks like. And given lots of data for different types of vehicles, it can learn to distinguish, for example, a Hyundai Ioniq 5 from a BMW or an Audi. So when it comes to we'll take that as background as we go into AI and software engineering and how they come together in the context of autonomous vehicles. It's useful to understand that in the world of autonomous vehicles, there's 6 really different levels of automation, from level 0 being no automation, to level 4, level 5 being high automation or full automation. And it's worth noting that full automation is not yet a solved problem in the world. So we are actively, as an industry, still working on this problem. There is no book you can go to or a set of research papers you can download that will tell you exactly what you need to do to create a fully autonomous vehicle. And we'll look at some of the technology that's in progress on making this a reality. Some names you might be familiar with. So Tesla, for example, is a well-known brand in the world of electric vehicles and autonomous vehicles. Tesla's FSD, or full self-driving software, is actually deemed to be at level 2 in the context of this model from the Society of Automotive Engineers. Their full self-driving model offers partial automation. There still needs to be a human driver present in order for the vehicle to operate. And that human driver needs to be able to take over at short notice in certain circumstances. Other brands or other manufacturers or self-driving car companies include companies like Zoox, Waymo, Cruise, Neuro, and Motional, which I'll talk more about some of these companies. These companies are operating largely what we call robo-taxi or shared ride services, where there is no driver in the deployed vehicles. So there may still be, and in all of these cases, there would still be access to a human through what we call a teleoperator. So if the vehicle gets into trouble, or if somebody in the vehicle needs to communicate with a human, there is still a facility to contact a human. But in the vehicle itself, there's no actual human driver. So that's one difference between partial automation and high automation. You may have heard of things like driver assistance and cruise control, and some of your cars may have these various features. Those sit on the left-hand side of this model. They're on the path towards full automation, but they're still very much in that partial automation phase or life cycle phase of the model. So what might we experience? So I talked earlier about better use of space, better use of our time as we use more and more autonomous vehicles, and these are being deployed in various cities in the world. Some additional benefits that we might see are improved traffic flow. So on the top there, you can see a model of traffic flow based on autonomous vehicles, and on the bottom, it's based on human drivers. So one thing we can do in an autonomous vehicle setting is remove things like traditional traffic control mechanisms, where we have the vehicles and the surrounding smart city infrastructure making the decisions at intersections, for example. So improved traffic utilization is another benefit that we can look to realize, and consequently that will reduce emissions. So while and optimize the use of fuel efficiency in the vehicles as well. So let's look at a particular use case. So we'll look at what we call a perception use case. And as we look at this perception use case, one difference between that's worth highlighting between, let's say, traditional software engineering and AI and software engineering is that we're really developing or entering into a new paradigm, a new programming paradigm. With classical programming, we're used to having rules that we develop and inputting data, and the programs that we develop produce answers. With machine learning, we input lots and lots of data, and we give our systems the answers, and the system learns to produce the rules that lead to those answers. So it learns over time to deal with new scenarios, unknown scenarios, apply the data, apply the example answers that it's been given, and develop new rules to deal with those situations. So what might that look like in the context of autonomous vehicles? So the use case that we'll look at is, again, what we call perception. We're looking to understand the intent of a vehicle. So imagine we're in a road space, we're in a shared environment with other road users. Our autonomous vehicle needs to understand what the vehicle in front of it is going to do. So we come to an intersection, and so the vehicle that we're interested in understanding is represented by the red shape at the intersection there. So we want to know, is that vehicle going to go left? Is it going to go right? Or is it going to go straight on? And There's a number of sort of finite things a vehicle at an intersection will typically do. And for the purpose of this example, we'll treat this as a classification problem. So we talked earlier about different types of problems we can address with or we can choose to classify our problem as. So we'll treat this as a classification problem rather than a regression problem, for example. What we want to do is understand from lots of data of intersections, what are some typical behaviors of vehicles at intersections, and we can model those behaviors. And the second picture here shows an analysis of data at intersections where you've got a couple of lanes at each intersection, and we've got vehicular traffic represented by the green lines, and we've also got, represented by the driving lanes, and we've also got a couple of bicycle lanes. You can see represented by the thinner blue lines. And with each of those, we're analyzing expected behavior, which is the green lines, and unexpected behavior, represented by the black lines. And the more frequently that behavior occurs, the thicker the line. So a very thick line for green represents a lot of expected behavior. A very thick line in black represents a lot of unexpected behavior. So unexpected behavior in this context might be, well, we thought the vehicle was going to go straight ahead, but it actually turned left, or we thought the vehicle was going to turn right, but it actually ended up going straight through the intersection. And we can see that there's a surprising, or maybe not surprising, depending on the roads you're used to driving on, but there's quite a lot of unexpected behavior when it comes to navigating intersections. So, from a classification perspective, we can look at the problem as as digging into understanding left turns, understanding lane changes, understanding right turns. These are some of the typical actions that might take place when we're at that intersection. Now, from a software engineering perspective, we can take and analyze that, and we can develop models to help our vehicles understand, well, what actually is going to happen at this intersection, not just with one car, but with lots of cars, with lots of vehicles, pedestrians, bicycles, other things on the road. So it's important to have infrastructure and tooling that enables rapid experimentation. So in this context, we want our engineers and scientists and other people in the organization to be able to focus on the problem that they're trying to solve. In this case, understanding the behavior of vehicles at intersections, and not worry at all about the data required to understand this, or how to create different scenarios. So the infrastructure that we'll look at a little bit throughout the session is designed to enable rapid experimentation. So we should be able to iterate on rapid experiments, train our models quickly, get some results, retrain our model, all without worrying about the mechanics of how do we load data, how do we analyze and interpret data, how do we validate results. So there's a lot of infrastructure required when dealing with something like AI and software engineering in autonomous vehicles. That infrastructure is very powerful and enabling in terms of what it provides to teams. So based on we'll use that infrastructure as well to basically help us play with the data, explore the data, generate or develop a deep understanding of the problem that we're trying to solve. Then, armed with that deep understanding of the problem that we'll try to solve, we'll develop a classifier. So again, we'll use 5 classes here. We'll say the vehicle can either turn left, turn right, go straight ahead, could change lanes to the left or change lanes to the right. So those are the 5 different classes we're using to predict the behavior of the vehicle. And we often talk about features in the context of AI. Features of the vehicle in this case might be things like the make and manufacture of the vehicle, the current location of the vehicle in the world, like maybe its GPS coordinates, the orientation of the vehicle. We might be interested in things like color of the vehicle. We might be interested in things like the current speed of the vehicle, those sorts of things. And when we're dealing with a use case like prediction in this case, some of those features are more consequential than others, for example. So obviously the current trajectory and speed of the vehicle is more impactful than the make, model, and color of the vehicle. So we can then use the infrastructure we talked about earlier to evaluate our model, and again, play with different scenarios, develop different scenarios within our use case for vehicle behavior, and understand how our model will react to the different behaviors of the vehicle that we're trying to understand the behaviors of. And there's again a rich set of infrastructure to support engineers in trying to understand that. One of the things that makes this type of scenario more difficult is that in the picture on the left there, I show a nice uniform intersection. It's pretty symmetrical, but a lot of our intersections, in the world in general, in Ireland in particular, maybe, are not always so uniform or so parallel. So this type of intersection where it's not a straight cross shape, for example, is what might lead our model to think a vehicle is about to turn left or right, but then it actually goes straight on. It's not that the vehicle was trying to mislead us or is driving badly. It's just that it's following the curvature of the road or of the intersection, and it looks for a moment like the vehicle is going to turn right, and then it actually follows the curve of the intersection and goes straight ahead. So when we talked about data earlier, it's important to build up lots and lots of data around different types of intersections and model the behavior of our vehicles for those different types of intersections. And the infrastructure again can show what's happening as different vehicles approach the road. It's a little difficult to read there, but what you're seeing in the bottom half of the screen are the probabilities of those different classes being true and being updated in real time as vehicles approach the intersection. So we don't always say the vehicle is definitely going to turn left. We might say there's a 40% probability that the vehicle is going to turn left, and as the vehicle gets closer to the intersection, that probability might go to 60%, 80%, or until the vehicle ultimately turns left, it'll be 100%. But the different classes that we talked about earlier have different probabilities at different points in time, and the infrastructure is designed to support our understanding of that data. And then finally, we can deploy the model in a vehicle, and on the bottom there you can see images being taken in from the autonomous vehicle, from the different sensors that we'll talk about in a little bit, and used to create a model of the world. And we'll talk more about how that happens in a few minutes as well. But in real time on the vehicle itself, there's a lot of compute happening as we try and perceive or interact with the world and build a picture of what's happening around us. So that model that we walked through and trained and evaluated is eventually ultimately deployed in a vehicle, and we can see examples of that interaction there in the bottom right. So why now? So why is autonomous vehicles, AI, software engineering have been in development for quite a while, but why now? What's special about this point in time, this period that we're in? And there are some factors that are helping us accelerate the state of the art in autonomous vehicle development, and one of those is availability of data, increasing compute power, the falling cost of storage. We'll look at some examples of the amount of data that's generated and the amount of storage needed to work with that sort of data. Advances in neural networks over the last couple of years, improvements in software infrastructure, and general advances in cloud mobility and robotics are all converging to make now, this period of time that we're in, a period of really advanced innovation in the context of autonomous systems driven by AI and software engineering. So let's look at some of the architectures that are making this possible. And so the Linux Foundation publishes this architecture roadmap on emerging edge applications and convergence of technologies. And if you look at the bottom row there, it's like a foundation of technologies that are enabling a lot of edge technologies, things like on-demand network function virtualization, hardware acceleration, AI, microservices, 5G. That entire layer is relevant and applies to the world of autonomous vehicles. And then you can see that that Linux Foundation identifies autonomous vehicles as one of the core areas for edge architectures and edge development. So we talk a lot about the emergence of the AI-enabled software-defined car. So there are, within the car itself, there are networks that communicate with each other. The car communicates with the infrastructure around it in terms of road infrastructure. In smart city development, there's a lot of infrastructure being developed for communication with vehicles. There's something called vehicle-to-vehicle communication, or vehicle-to-infrastructure communication, or V2X, vehicle-to-everything communication. So all of that is I suppose adding to the context of autonomous vehicles and things that we need to be aware of as we develop autonomous vehicles. So the car itself, or the architecture of the software, moving from a model of more individualized, what we call electronic control units. In a traditional car, there are maybe dozens or hundreds of electronic control units, to much more of a software-defined or service-oriented architecture with lots of new factors for differentiation. And specifically in the context of autonomous vehicles, we're deploying lots and lots of sensors on vehicles. So you'll hear things like cameras, LiDAR units, radar sensors, IMUs, GPS, lots of different sensors that are used to help the car understand the world around it and to make sense of the world around it. So the major subsystems that we care about, and just in the context of the use cases that we'll look at today, are things like the sensors subsystem, perception, planning, and control. So sensors are things like we just looked at: cameras, LiDAR units, radar units. Perception, we looked at the use case a moment ago. With perception is about taking all of that input data from the sensors and trying to make sense of it to understand what's actually happening in the world, and then make predictions about what the car should do next. And so that leads us into the planning subsystem. Planning is all about plotting a route in the world, or deciding what to do, and then control is where we actually manipulate the controls of the car to move forwards, backwards, slow down, speed up, turn left, turn right. All of that is managed by the control subsystem. Typical architecture might look like this. So this is bringing AI and software engineering together in the context of the architecture for a vehicle. You can see cloud services. We typically have data platforms and remote services that the car communicates with. There are application level layers. It helps to think about this in terms of layers. There's an application layer with the major subsystems that I just talked about. There is a middleware layer, typically running operating systems or running frameworks like ROS2, which is a robot operating system that sits on top of things like Ubuntu. And that's basically messaging-oriented middleware layers that are present in vehicles. Then there's the operating system, and usually multiple operating systems are present in vehicles. And these are obviously real-time operating systems like QNX and Ubuntu. And then there's the hardware that's deployed as part of the vehicle, things like compute units, sensor units, the control units, and so on. And usually in the trunk of or the boot of a self-driving car, there's a big compute unit with all of these things. And in terms of behavior, well, we won't go through this in detail, but just to give you an idea of the interactions, data comes in through the sensors. It's often combined with 3D mapping technology to help the car figure out where it is in the world, localize its position, and then some typical things we want to do with the vehicle are detect other objects or track their behavior, or plan a route and navigate from A to B, and basically continuously update the car, the car itself to turn left, right, accelerate, decelerate, and so on. So again, there's some key parts for how those subsystems integrate with the other parts of the car. Again, we won't go into too much detail on those, but just be aware there's a lot of software components that are continuously interacting as the car navigates the world. So another example use case here is the, so we looked at the prediction use case earlier. Let's look at the perception use case. As our car is moving along, it will see some activity ahead. In this case, a bunch of children that are in a park near the road. And using the different sensor data from videos, LiDAR and radar, it will combine the data from those different sensors to basically build up a picture of what's going on in the world, to create the vehicle's model of the world. And so it will take all of that data and create a perception called children playing ball near the road 15 meters ahead. Now, with that, it will try and assess the likelihood of a child following a ball onto the road, or if the ball is moving towards the road, or if any of the children are moving towards the road. It will perceive that and adjust its path. The vehicle will adjust its path accordingly. So why do we have multiple sensors in the car? Well, generally, they each have different strengths and weaknesses. So radar, for example, is really strong at measuring the range or measuring the distance to the car in front or to other objects in the environment. Cameras are very good at classifying objects, whereas radars are less strong at that, excuse me. LiDARs are very good in dark conditions or poor weather conditions. So there's a term called sensor fusion, which basically means we fuse together data from these different sensors in order to create a picture of the world. So these hardware sensors are deployed on the cars. With the software on the cars then combines all of these sensors. And it doesn't necessarily always work perfectly. So here we see an example of the perception system in an autonomous vehicle looking at the world, thinking it detects lots and lots of traffic lights, but what's actually happening is there's a truck in front of it carrying some traffic lights, and it's picking up on that. So this is an autonomous vehicle, as you can see, driving at 140 kilometers per hour along a motorway, and thinking that it's seeing lots and lots of different traffic lights coming at it very quickly. So let's look briefly at some of the technology stacks and tools then that are enabling this, and even just looking at the Linux Foundation again, you can see there's an overwhelming array of machine learning, deep learning tools, security and privacy tools that all come into play. So if you're interested in this space at all, this doesn't apply just to autonomous vehicles. It's worth checking out the Linux Foundation's AI forum on all of these different tools. And we would typically use a subset of these in autonomous vehicle development. So in terms of the type of technology stack that we might experience in autonomous vehicle development, it's useful to think about it in terms of algorithms, software, and hardware. So algorithms might be things like single shot detection, we're using for detecting, or YOLO, you only look once. These are different algorithms we might use for detecting objects in a scene, through camera sensors. So think about algorithms as being one layer in our technology stack. Then in terms of software, it breaks down into things like frameworks and libraries. So typical frameworks might be PyTorch, TensorFlow, XGBoost are typical frameworks that we use in the development of these systems. And then there's a lot of different libraries, like radar and LiDAR typically work with something called point clouds. So there are point cloud libraries that we use in interpreting the data from radars and LiDARs, for example. OpenCV is a very popular computer vision library. NVIDIA develops their CUDA language and libraries that have a lot of application in autonomous vehicles, and so on. So the point here is there's a lot of different libraries that are useful in the context of developing these systems. And a really interesting area is in this area of accelerators. So our typical desktop PCs or laptops or MacBooks, typically use the central processing unit or CPU as the main brain of the computer, and that's evolving, of course. But for AI specific use cases, there's a lot of different accelerators or chips or system on chips that are being developed to help with the autonomous vehicle use cases. And you'll see things like GPUs, for example, are used quite a lot in AI. So graphic processing units, which are great at handling large matrix multiplications. Are quite well known, but there are other ones like tensor processing units, video processing units, which are great for optimizing video use cases. There's neural processing units, and of course, variations on FPGAs are all available to optimize different use cases. So in terms of the different roles that we see in organizations, we might have our ML engineers or software engineers or data scientists focused on developing algorithms for like the prediction use cases or perception use cases. We might have framework developers focused on using the frameworks and libraries that we show here, and different library developers and hardware engineers and roboticists might be more focused on the hardware end, developing things like accelerators and the connection technology used in the vehicles. So in terms of infrastructure, a typical ML workflow looks something like this. I mean, if you work with machine learning in other environments like not autonomous vehicles, this will be familiar to you as well. Typically, we start with understanding our model requirements, collecting lots and lots of data, doing some feature engineering, model training, model evaluation, and monitoring. So basically the use case that I walked you through earlier, this is a formalized version of that workflow, basically. And some challenges that we want to manage through developing software infrastructure. Well, it can be very difficult to keep track of all of the experiments that we want to run in autonomous vehicles. So we need a way of cleanly managing all of the different experiments. It can be difficult to reproduce code. We want to have a standard way of packaging and deploying our models. We need to have a central store to manage our models and share models across the team and keep a history of models. So these are some challenges that we want to address, or we need to address in the context of AI and software engineering. Subject, our ML applications are, we say they're subject to change along these three axes: code, model, and data, and it's useful to think about it in those terms. So there's a few slides here that I'll just go through very quickly. They're really just there as background, and you're welcome to have the slides afterwards. But there are some challenges under each of the categories of development, production, and even organization challenges that it's useful to be aware of. Experiment management we talked about already. Troubleshooting, resource limitations are all common development challenges. In the context of AI and software engineering applied to developing autonomous vehicles, this picture shows roughly the breakdown of what types of software, or what's our focus in terms of developing software for let's say the proportion of our overall effort. So you can see at the top there that roughly 15% of our overall development effort is on the autonomous car sensor and software. All of these other things are still critical in the context of developing systems. So we need to pay attention to cyber, to navigation and mapping, machine learning. There's some OLP work that takes place as well, and the car's connectivity and communication, both within itself as a system and with the outside world, accounts for roughly 20% of the effort. So quite a lot of areas there. And a well-known picture here that's still worth emphasizing is the proportion of let's say code in the overall development of a system. So even though we're talking about AI and deep learning and software engineering, it's worth emphasizing that constitutes a relatively small proportion of the overall code that's involved in the development of large complex systems. So you can see that little black box in the center there is proportionally how much of the code we're talking about in terms of machine learning code. There's still a lot of code required for infrastructure, for feature extraction, for analysis and some monitoring and so on. So we'll talk just very briefly about evolving DevOps to manage machine learning systems. Basic point here is that continuous integration and continuous delivery and continuous training are essential to the operation of this type of system development. And machine learning operations, again, a popular a set of practices that have developed over the last couple of years are essential in development of these systems. So some of the benefits that ML Ops brings are, and basically it's really about integrating your machine learning life cycle with your overall system development life cycle, so that we can increase our productivity. We're not wasting time or effort with missing data or trying to track down experiments, for example, or trying to figure out what hyperparameters we used yesterday on a particular experiment. We want our entire life cycle to be repeatable, reliable. We need it to be auditable, so that we can have versioning of our different inputs and outputs, and we want to have high data and model quality. So basic ML Ops level 1 might look something like this. Goal is basically to perform continuous training of the model by automating the pipeline. But really we want to have, that's a good start and a good foundation. But we want to take it beyond that and have a CI, or continuous delivery system, that helps us rapidly explore and experiment and iterate through many different types of experiments very quickly. So complementary model here is what we call continuous delivery for machine learning, and it's basically a software engineering approach that allows cross-functional teams to collaborate through that entire ML workflow lifecycle. And again, it's emphasizing the different areas of focus for data, model, and code that we talked about earlier. Some other tools that we use in this context are things like DVC for version control, MLflow for managing the life cycle of machine learning use cases, and various other things. So some considerations to think about when building. It's useful to distinguish between when are we in the research mode and trying to figure out what's the optimal set of hyperparameters that we're trying to develop for our models, versus when are we developing our systems, and what are our unit and integration and acceptance test practices, for example. And then what happens when we're in production? How do we use things like canary releases in the context of autonomous vehicles? How do we use observability in the context of autonomous vehicles? Different test pyramids. Again, we're dealing with safety critical products. Lives are literally at stake in the context of these systems that we're developing. So all of these test pyramids and that we talk about in other domains in software engineering are still relevant in the context of these safety critical systems. And we can talk about everything from exploratory tests to unit tests. But the main point of this picture is it's useful to distinguish between tests focused on data, tests focused on the model, and tests that are focused on code, and then integrate those for our whole system. So we can, again, characterize technical debt in AI-based systems. Useful to be aware of these different categories of debt that occur in AI and software engineering intensive systems. Big one tends to be infrastructure debt, tends to be the most recurrent type of technical debt, followed by architecture debt, code debt, and test debt. So our software engineering strategy needs to account for that and be continuously attentive to the types of debt that we're accumulating. So some typical challenges that we see in these systems. Won't go into a whole lot of detail on these, but you can see AI and software quality is a huge one. Testing continues to be a big challenge. Infrastructure, data management, and so on. So the size of the colored squares here show basically the proportion of these types of challenges. And there's a useful research study that you can refer to for more detail on these. Another thing that's still evolving is, well, what is an AI engineer? As more people move into this space of AI and software engineering across different domains, we see a lot of diversity in the definition of the job description. So there's a useful research study here that identifies different types of job titles and different areas of focus for people working with AI and software engineering. Another big challenge is dealing with generally the amount of data that we're generating. So one autonomous vehicle can generate up to 4,000 gigabytes of data each day. And a lot of that data is coming from the different cameras and other sensors that are deployed on the vehicle, and also from the vehicle's interaction with the world around it. Public perception is still a continuing challenge with autonomous vehicles, and building trust in society that people believe autonomous vehicles are safe to use is an ongoing challenge. Public policy and laws are still evolving, and they're not always consistent. So they do vary from country to country and even from state to state in some countries. And a couple of final thoughts. The ML bugs, or Greg Brockman is the founder and president of OpenAI. He says ML bugs are so much trickier than bugs in traditional software, because rather than getting an error, you get degraded performance, and it's not always obvious beforehand what ideal performance should be. So ML debugging works by continual sanity checking and comparing to various baselines. So 3 focus areas: remember algorithms, product design, and the system that you're developing. Be aware of the societal impact of the technology. Understand who benefits from the systems we're developing. Is this something that we should be developing? Is this genuinely bettering the world? These are good questions to ask for AI and software engineering systems in general. And so in closing, just a reminder that these are safety critical systems. Details matter. We're using AI and software engineering to interact with people and objects in the real world. And from a technical perspective, a self-driving car is many, many things. It's an intelligent autonomous system. It's a mobile robot. It's a data center on wheels. All of these things present many challenges and opportunities for software engineers. A really interesting place to get started is if you're interested in this without developing a full self-driving vehicle, AWS actually offers this Deep Racer vehicle, which is a 1/18th scale car with all of the sensors that we talked about. But you can actually train your models, deploy your models, and even compete in competitions with your 1/18th scale autonomous vehicle. And with that, thank you for being here, and hopefully we've got a couple of minutes for questions.
Thanks so much, Ken. That's such interesting information. Thanks for sharing that with us. I would love to see this, hit us in reality, these self-driving vehicles. I keep imagining them on these small country roads in Galway or Mayo, yes, and seeing how that will work with the tractors and all that. But we do need to wrap up. I think I'm just going to get one question in that came in the Q&A from the audience, and then maybe if I can put your LinkedIn profile here, maybe people can reach out to you there.
Please, absolutely. LinkedIn, email, whatever works for people. Yeah.
Okay, so Jerry Carty asked a question. He said, what, in your opinion, is the biggest obstacle to moving to level 4 or 5 of vehicle autonomy? What breakthrough do we need in AI in order to advance?
Yeah. So part of that is just the so we will get there, and we will get there, definitely in a reasonable amount of time. But I would say there's no one single big breakthrough, but one is just the how we process and understand the sheer amount of data. So the first use case I presented, for example, lots of data from different intersections is useful to help us understand how to navigate intersections. There comes a point in time where having data about let's say one more Audi or BMW navigating an intersection is not as interesting as, let's say, somebody coming on a unicycle and juggling and going in front of your vehicle. So diversity of novel data is really useful in strengthening our models to help us navigate uncertain conditions. That helps that develop is actually just to pick one example, there's a lot of work in developing simulators in the context of autonomous vehicles. So using the same technology that's used in video games. So we use game engines like Unity or Unreal, for example, to develop artificial worlds to help train our models in self-driving vehicles. And through those we can, we're only limited by our imagination in that context. So we can create, we're not reliant on what actually happens in the real world to train our models. We can create all sorts of scenarios to help train our models using things like simulators. That's a very active area that's helping enrich the pool of data that we can use to train our models. On the other side of it, I'd say one thing to add to that would be probably the biggest barriers will outside of the AI directly will be the public perception of AI and government's policy in supporting infrastructure in deploying AI-based systems. So I'd say those areas will definitely they're definitely actively being worked on, but will definitely lead to the sort of breakthrough level 4, level 5 improvements that you're asking about.
Thanks so much, Ken. I think we're going to have to drop it there today. So we hope to see you on many more events. There's plenty coming up for the rest of this week. Just follow the program. I'll put the program link in here, and then we'll see you then. And Ken, congrats on your new job. I hope you have a great first day. Thanks for making the time for us today. We really appreciate it.
No, my pleasure. Thank you, Taryn.
Thanks, everyone.
And thanks, everybody.